Assalamu alaikum, my dear students. How are you? Hope you will be fine and okay. I welcome you all in my into my today lecture. Today is our 36th lecture, and today topics includes the Hooke law, stress strain curve, mechanical properties of solids, the strain energy and strain energy per unit volume. So let us start with the name of Allah Almighty. The Hooke law, as I told you in the previous class, that the Hooke law actually determine the relation between stress and strain, and the Hooke law tells you that the ratio of stress to strain always remain constant within the elastic limit within 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 the elastic limit within the elastic limit the ratio of stress to strain always remain constant for the given material, always remain constant. This is known as Robert Hooke law, right? It is always remain constant. So Hooke law tells you that the constant, this constant equals to the ratio of stress to strain depends on the type of the stress and strain. Here our main theme of the lecture is to determine, because Hooke law you have already studied in class 9, that we want here to study the stress strain curve, the stress strain curve. Here we have the stress strain curve for the given material. Here you see, look, this is the stress strain curve for ductile material. Stress strain curve. Usually this stress strain curve is for ductile material. Ductile material or substances usually, which can be drawn into thread or sheets. So here in this diagram, look, this is the stress, and this stress is in Newton per meter square, and here we have the strain produced in the body. So here you see that from the point O to the point A, you see that there is a linear relationship. You see here there is what? A linear relation. There is a linear relationship between the stress and strain, So here if you see that if you increase the stress, the strain increases, right? So for the same rise in stress, there is the same increase in the strain also. This happens till point A, right? So that is what we call this point as the proportionality limit. Proportionality limit, right? And this region we call here as the elastic region. This region I would like to, this is called which region? The elastic region, right? Or the elastic deformation. Why? Because here the stress strain curve remain, that is the stress strain ratio remain constant. It remain constant. This region, sometime I call this as the Hooke region. Why? Because in this region, the Hooke law is obeyed. So this is called which region? This is called the Hooke region. The Hooke region. We call it what? We call it the Hooke region. This, the stress strain curve varies from material to material, right? This may be, but from O to A, this ratio will always remain constant, though different for different material. Then here you see that beyond A to B till the yield point, this is also called this yield point. This is also called the yield point is also called the elastic limit. This is also called the elastic limit. Here, once you cross the elastic limit, the body is unable. The body is what? The body is unable to regain its shape and size. To regain its shape and size beyond what the beyond the after when the deforming forces removed. So here you see that, look, here this is this region is actually we call the plasticity region. Even though you just see, look, here the relationship is not constant, right? Look, there is no direct linear relationship, but still till this yield point within this region, this is just the body can still regain its shape and size. This could also be within the hook region, okay, but not that much very quick, but still in this region there is the possibility of regaining its original shape and size, right, within this region like this one. But here, once you cross the yield point, the body is unable to regain its original shape and size, and there occur permanent deformation. There occur what? There occur permanent deformation. The permanent deformation, there is the during this the body here, that is after once you cross the elastic limit, then the body is unable to regain its original shape and size. So this region we call the plasticity region. This is called what? This is called the plasticity. This is called the plasticity region, right? The body is unable to regain its original shape and size after when the deforming force, after when the deforming force is removed. So this is the region of permanent deformation, right? This is the region of what? This is the region of permanent deformation for the Hopla. Now, the point C here, this point C I called here the, this is called the UTS, ultimate tensile stress. Oh, sorry, the UTS, the ultimate tensile stress. Right, the first, now just as I told that there is the hook region, there is the plasticity region, and then I will now discuss the region beyond C. We call that point the UTS, but here I just want to tell you that here we call it stress. This is the corresponding stress for the yield point, or the elastic limit is known as the yield strength or the yield stress, right? The ultimate tensile stress, it is the maximum stress the body can endure, or the maximum stress the body can withstand, the body can withstand without breaking. Without breaking. This is called the ultimate tensile stress. Right now, that is beyond which there occurs necking. Once you cross the UTS, there occur necking. This is called the necking. You just see, look, the body develops neck if you increase the stress further until the point D, which we call the fracture or the breaking point. Here you see. So this is the necking region. And this is usually, the necking region is for the ductile material. When the material is brittle, it will break without gaining the necking, right? So this is the necking region, right? And that is the, in the UTS, I would like to tell you for the UTS, that for the UTS, the stress, that is the the even if you remove the deforming force, if you make the stress zero, right, but the strain will never be zero. The strain will what? The strain will never become zero. There will occur a permanent change, right? And the necking will then start. Now look at the point C and D. If the point C and D, if the points, if the points C and D are very close, to each other, then what will happen? For the close point C and D, the body is said to be brittle, right? The body is said to be brittle means that once you cross the UTS, it will suddenly break without developing any necking. Suddenly break without necking, right? There will be no necking. If the point C and D are far apart on the graph, far apart on the graph, as you see here in this case, in the case of the ductile material, then what will happen? The body will develop necking and the material will be set to ductile material, right? That is, that it will start elongating, right? That is increase in the length as you see here, right? And such material are said to be ductile and they can easily be drawn into threads. For example, gold is the best example. It is so much ductile that if you have 1 ton gold, you can draw it into threads which can cover the distance between moon and earth. So that is all about the stress strain curves for the Hooke law. Then the next topic is, the mechanical properties of solids. Mechanical properties, mechanical properties of solids. Mechanical properties of solids. Now, what are the mechanical properties of solids? The mechanical properties of solids are those properties of solids which describes the strength, and resistance of the material, and the resistance of the material to deformation, to or to strain, to deformation once the deforming force or stress is applied. Or we can say that the ability of the objects, the ability of the substances or material to withstand stress. These are called the mechanical properties of solid. These properties include the strength of the material. The first is the strength. Now, what is the strength of the material? The ability of the material to withstand stress, to withstand, to withstand stress. It depends upon the nature of the material. For example, the strength of the steel is more than the strength of the iron rod. So it is the first property. The second property is known as the hardness of the material. The hardness. Now, what is the hardness of the material? It is the measure of the ability of the body to stretch, right? That is the hardness, that how the material is able to stretch. That is what the sorry, I think hardness, that is the hardness of the material is not that is to for stretch, rather it is for the scratch. I would like to, that how it can resist scratch. For example, like in these days you see that some smartphone advertisement, that unscratchable glass screen, right? So that is how the material is hard to be scratched, right? And that is the, for example, the hardest material I would like to tell you is the diamond, right? Or high carbon steel. Diamond or diamond, non-scratchable. Diamond are we some are high carbon steel. High carbon steel are non-stretchable. Right, non-scratchable. Sorry, sorry for this. I just say stretch because stretch is most often used. The second important point is the brittleness. The brittleness of the material is the tendency to break easily or suddenly without gaining necking first. So the ability of the material, the ability to break easily, to break easily developing without developing any necking, right? That is the point CD close. So glass is one of the best example for brittleness. High carbon steel, for example, car bearings can be broken without necking. Ceramics, right? They are the examples of what? They are the example of the brittleness. The fourth The fourth one is the toughness. Toughness. Toughness is the ability of the body to absorb impact or shocks. Shock absorbing ability. Shocks or impact absorbing ability of the material, right? Which is just opposite to the brittleness. Okay, so that is the brittleness. The next one is the fifth point is the plasticity of the material. Plasticity, right? Plasticity, the material which deforms permanently when small forces are applied. This shows plasticity. Plasticines and clay are the good example of this. And then another one is the elasticity of the material. Elasticity. Elasticity is the property of the material in which they are how quick they are to regain its original shape and size right after when the deforming forces are removed, right? The example include rubber or steel or kind of substances like these. And seventh property is the stiffness. The stiffness of the material. The stiffness of the material, sorry, to resist bending. To resist what? To resist bending. For example, you know, steel or irons are, the steel is brittle. So for this reason, like in building or in structure, we need stiffness, that is which can resist the bending. So for that purpose, we use the concrete, right? So concrete has the ability to resist the stiffness. Number 8, ductility. Ductility. Ductility is the ability to draw out into wires or threads, right? For example, gold is the best ductile material. Similarly, there could be other properties also like malleability. For example, substances which can be drawn into sheets like aluminum, they are called the malleable substances, right? So they all depends on the nature of the substance. So these are the few mechanical properties of the substance. The next one is the strain energy. The strain energy and the strain energy per unit volume. Strain energy in objects. The strain energy and strain energy per unit, strain energy per unit volume of an object. Now, what is the strain energy? Strain energy, it is the energy stored in the body or objects or substances due to strain. Due to strain is called the strain energy. Mathematically, the strain energy of the body is equal to the strain energy of the body is given by the equation. This is given by the equation, the strain energy. This strain energy, the strain energy of the body, the strain energy of the body is equal to 1 over 2 F into E small e, where E is the extension. This is the force applied per unit area, and this is what? And this is the extension. So let us see here that how we can get into this equation. The strain energy, this formula, the strain energy relation can be derived from the force extension graph. Here you see the force extension graph for the material. This is the force and this is the extension here. Now you just see, look, for example, when you increase the force, look here, that is you just see, look at this force. First let me explain to you this by using this diagram. Let us suppose, for example, if we have a rod and the rod has length L, right? And this is the length, the original length of the rod. Clear? And if you apply the forces on the rod of cross-sectional area A, then what happens? The rod stretches and the extension produced in the rod, that is the change in length produced in the rod, is this. This is this E small e, right? And this is the force, and this is this force, right? So the length of an object increases, and we have this as the L dash. So we know that the work done on the stretching the wire, that is this work done. Now the work done on the rod, the work done on the rod while stretching it is equal to what? It is equal to the average force. This work done is equal to the average force into the extension reduced in the body. Extension, this extension, that is what? The displacement, actually it is cast, and the extension produced, it is this extension or elongation in the rod produced. So you know that this work done, because you already, first of all, let me tell you that how we can do for this average force, how we can find the average force here. You know that right in the beginning, when the average force, that is when the initial force is 0, then there is no elongation in the object. The elongation is also 0. Yeah, the extension in the, that is right, the from the initial condition here, you see when the force is 0, the initial force, no force acting on it, then the elongation or the change in length is 0. This change in length, delta x, I just say this is x. This is what? This elongation or the extension is 0. But when you apply a force, let's say the final force, when you increase the force to F, right, then what happens? It causes elongation that is denoted by small l. So what is the F average force here? The average force will be the force initial plus the force final divided by 2. So here you see that it is 0, and here you see that it is F by 2. So the average force, we F, it becomes equal to F by 2. So this is the average force that acts on the system. Now you know that when you do work done on the body, it's increase the mechanical energy of the body. So this work done will appear as in the form of stored energy in the body, and we call that stored energy as the strain energy. So this strain energy in the body will be equal to F by 2 into the extension produced, which is E. So it will be equal to F by 2 into E. Sorry, more good is like this, 1 over 2 F into E. This is the strain energy, the energy stored in the body. Now you can express this in number of ways. For example, look, strain energy. This strain energy can even be expressed in terms of what? Stress strain. For example, let us see that what is Young modulus. Young modulus is the force per unit area, the stress to strain, right? The stress to, let me do it here. Young modulus, stress to strain. So force per unit area of an object, and strain is the change in length to the original length, right? The change in length. So E into, this will be E into, I'm doing things very direct, I'm sorry for that. Force per unit area and the change in length to the original length. So it will be FLE into, that will be E into A, the Young modulus, like that. So now you can replace the FE like that. For example, let you multiply both sides by E, then Young modulus into this into F E L, and that E will be going there, it will become L square, and this will become L. So what it will be happening like this, that in term of what? That in term of Young modulus, this will equals to, sorry, the area will be there. It will be like this. So you see here that we have the strain energy stored in the body will be the product of the Young modulus of the body into area into the change in length, square of the change in length into L like this. So this is in term of the Young modulus. So you can calculate the strain energy or the energy stored in a body like this. The energy per unit volume of an object, this is the strain energy per unit volume of an object. So this can be done by what? The strain energy per unit volume. Strain energy per unit volume of an object. Volume of an object. So this strain energy per unit volume of an object is the strain energy ratio volume of the object. In our case, the volume of the solid. So it will be equal to S1 over 2 F into elongation. And you know the volume of the object will be 2. It will be the volume of the object will be uh, area into the length of an object AL. So this will come out to be like 1 over 2 F into A into E by L, like this. So as you see, look, this is nothing but it is 1 over 2, and this is the stress, and this is what, and this is the strain, longitudinal strain, like this. So that is the strain energy. So the strain energy per unit volume is always the product of what the half times the stress and strain produced in the object. So this is our today lecture. Thank you for being here, and inshallah see you in the next lecture where we will discuss the most important topic, the energy band theory. So we'll see you there, inshallah.